Hello and welcome to Math with Mrs. Becker. This is Pre-Calculus. Today we will be studying Chapter 1, Section 1, which is titled Real Numbers, Relations, and Functions. Today we are going to study key terms such as sets of numbers. We will look at the coordinate plane, discuss relations, determine the difference between input and output, as well as domain and range, and also study functions. To conclude the section, we will use function notation to evaluate some algebraic expressions. Without further ado, let's get started. Lots of times when people are asked what is mathematics, it's very hard to try to give it a definition. Well, here's one possible definition you can use. Mathematics is the study of three particular things. Those three things are quantity, order, and last but not least, relationships. So one good definition for what mathematics is, you could say mathematics is the study of quantity, order, and relationships. This first chapter of Pre-Calculus, we're really going to define real numbers as well as take a deeper look into the coordinate plane. In Chapter 1, we will use the vocabulary of relations as well as functions to begin the study of mathematical relationships. The number patterns in recursive, arithmetic, and geometric sequences are also examined, and we will examine these three different ways. We will examine them numerically, so using numbers. We will study them graphically. We will actually create graphs to look at these sequences. And last but not least, we will look at them algebraically, which means we will create equations that we can use in a sequence to know what the next number would be. So again, in Chapter 1, we will study sequences, recursive, arithmetic, and geometric. And as we study each type of sequence, we will look at those sequences using numbers, so numerically. What do they look like graphically? And then creating an equation algebraically. We will also review lines and linear models. So right away, let's start talking about real numbers. Now, I know in order to be in Pre-Calc, you have worked to a level where you were introduced to the imaginary number. Remember, the square root of a -1, by definition, is I. It is imaginary. Well, anything that is not imaginary is a real number. Real numbers can be pi, fractions, decimals, the number 5, the number 527,000. Okay, those are all real numbers. You have been using real numbers most of your life. The subset of real numbers, and what that means is that within the real numbers, because it's such a wide array of values, there are different sets, and those subsets are rational numbers, irrational numbers. Every number is either going to be rational or irrational. And the best way that I remember this is if you're thinking about having a conversation with a friend, if it makes sense, it would be a rational conversation. Well, to me, rational numbers make sense. They either terminate, meaning that they have a stopping point, or they have a repeating pattern. You know what's coming up. Now, irrational numbers, if you can think of a time when you had a conversation with somebody and it was just irrational, that means it went on and on and on forever and ever, and you had no idea what was going on. Probably recall a time when somebody called you to vent. Irrational numbers, it's kind of the same thing. What happens is the number continues forever and ever and ever. It has no end. But unlike rational numbers, there's no repeating part. You have absolutely no idea what is next. Okay? Integers, whole numbers, and natural numbers. So we're going to go ahead and discuss those a little bit further. Let's take some time to review these subsets. And it says review because this is something that we did look at in Chapter 1 way back in Algebra 2. Okay? So rational numbers, again, the way that I remember it, to me, they make sense. It's like a rational conversation with somebody. It could be like 7 over 2 because 7 over 2 is 3.5. That stops. It could be 1/3 because that's 0.3333 and it repeats. It makes sense. Now, irrational numbers, they never end and there is no pattern to them. So again, think of that conversation where somebody calls you to vent and you're like, I don't even know what you're talking about right now. An example of an irrational number would be like the square root of 2, and I'm going to show you what that looks like on a calculator. So if I go the square root of 2, notice this. It takes up the entire calculator and the decimal part. 4142135662. I have no idea what is next. Okay, if I go the square root of 7, that's another irrational number. If I put that on the calculator, it takes up the whole thing. 645751311. There's not a repeating pattern there. So those are two examples of irrational numbers. Every real number has to be rational or irrational. So right here, they're going to have us create a diagram. So the first thing I'm going to have you do is we'll just start off and make a really big rectangle. So this rectangle represents all real numbers. Every real number has to be either rational or irrational. Okay, and so that's what we have so far for our diagram. Now, integers, if you remember from Algebra 2, if you had me in Algebra 2, I talked about integers as football numbers. When you watch a football game, you can have negative values. Maybe the quarterback got sacked, or you fumbled, or there was a penalty. But there are situations where the ball could go a negative amount of yards. In football, you can have 0 yards. Between two different plays, the ball might not move at all. You can have positive values if you have a successful running play, or you have the quarterback throws the ball and your receiver catches it, okay? So in football, you can have negative values, 0, or positive values when you're talking about how many yards the football moved. One thing you do not see, though, there are no decimals. And so integers, that's the next type. If you have a real number, if it's rational, it might be an integer. Sorry, I'm talking right at the same time. Okay, so if it's a real number, if it's irrational, you're done. It can't be anything else because it doesn't make sense. If it's a rational number, now remember, rational numbers, you can have fractions, okay? 2/3 is 0.6 repeating, so it makes sense. You can have the square root of 4 because that's 2, it stops. We can have 7 over 2, that's 3.5. But these values are not integers because when you're talking about integers, there are no decimals. Now, whole numbers, again, if you remember from Algebra 2, I called those the donut numbers. And the reason why is because if I have that value, in order to create a donut, you need to punch out the donut hole. At this point, this number looks like a 0. Whole numbers start at a 0. So there are no negative values. And again, there are no decimals. So if you have an integer, integers can be -1, they can be 0, they can be 4. Okay, they can be any numbers, positive, negative, or 0, just no decimals. But if you have an integer, as long as it's 0 or higher, it can also be what's called a whole number. So that's a whole nother category. 0, 5, 8. You just cannot have any negatives. Well, there's another type of number that's called the natural numbers. I look at those as counting numbers. And the reason why that helps me is because if you walk up to a young child and say count, natural numbers are the numbers that are natural for them to count. They start at 1, 1, 2, 3, 4, and ... As you get more comfortable counting, you can go higher and higher and higher. But again, here we see no 0. It eliminated that 0 because when you ask a young child to count those natural numbers, they don't start at 0. They start at 1. So if I'm looking at natural numbers, and I want to make sure I don't get these two confused, there are no zeros. There are no negative numbers. There are no decimals. Okay, so natural numbers are like 1, 2, 3, and it keeps going. The cool thing, when you have a real number, if it's rational, it could also be an integer, a whole number, and natural. It can be all of those things. But if you have an irrational number, like the square root of 7 or the square root of 2, it's done. It can't be anything else. So just to make sure that we have our head wrapped around this, true or false, all natural numbers are whole numbers. Okay, so every natural number, we want to see if that would fit for a whole number. And remember, a whole number starts at 0 and then goes up. So there's no negatives, no zeros. Natural numbers are 1. Well, 1 fits there. Yes, it's right there. 2, 3. So that works because natural numbers just start at a 1. The only difference between the two is that whole numbers include a 0. Natural numbers do not. So every natural number does belong to the set of whole numbers. Cool. All rational numbers are integers. Well, integers are our football numbers. Remember, there's no decimals. Well, rational, 7 divided by 2 is 3.5. That's rational, but you can't put 3.5 here because that's a decimal. Square root of 4 is 2. Hey, that would work. 2/3 is rational. It makes sense. It repeats 0.666666 going forever and ever and ever. But that doesn't work as an integer because it's a decimal. So that particular one would be false. All whole numbers are rational. Now, rational means it makes sense. It either stops or it repeats. So whole numbers are, they start at 0. 0 makes sense, it stops. 1 makes sense. 2, 3, 4, 5, 6, 7. All of those numbers are what you call terminating. They have a definite ending. So the first thing we really wanted to make sure to repeat or to review from Algebra 2 is that when you have numbers, there are lots of different subsets. It's kind of cool. So starting off this pre-calculus year with just some vocabulary review. Okay, now the real number line. To me, this is so fun. Okay, think back to like 7th and 8th grade when you just barely started graphing and you started off on a number line and then that grew into a coordinate plane. That's what we get to do today. It says the real numbers are represented graphically as points on a number line. Let's draw a real number line below. So we're going to draw a number line. And I'm going to have us doing some graphing on that number line. So we're going to go from -6, go all the way up to +8. -6, -5, -4, -3, -2. I hope you guys are having a good time. -1, 0. 1, 2, 3, 4, 5, 6, 7, 8. I have a little extra room, and if you're like me, that's going to bug me, so I'm going to throw a 9 on there. Okay, it says when you are graphing on a number line, every single point, it has a special name. That point is called a coordinate. Now, when you are graphing on a number line, one thing you have to realize is that it is okay to plot points that are not exactly at these intersections. Like if I have 8.5, I'll have a coordinate or a point in between 8 and 9. So we're going to go ahead and graph the following points on our real number line. -5.6. So I go to the left because it's -1, 2, 3, 4, 5, and 0.6. So a little more than halfway to the 6. That is -0.56. Oftentimes, when you have a fraction or a square root term, if you are going to graph it on a number line, it's going to be helpful to look at it in decimal form. -7/2 is the same as -3.5. So 0, I go to the left 1, 2, 3 and a half units. This is where -7/2 would be. Now, if I'm looking at the square root of 7, oh, funny, that was actually on there and I deleted it. Square root of 7 is approximately, because it's irrational, so I'm going to round it, 2.65. So 2.65 is approximately what the square root of 7 is. So from 0, it's positive, so I go to the right 1, 2, and more than half, that's the location for the square root of 7. 33 divided by 7, just as a reminder, to go from a fraction to a decimal, you take the numerator, in this case 33, divided by the denominator. Again, I'm going to go ahead and round this. This is approximately 4.71. So if I am graphing it, start from 0, it's positive. So go to the right 1, 2, 3, 4 whole units, and 0.7, so pretty darn close to that 5. That coordinate represents 33/7. And last, this is in decimal form. So I go to the right 1, 2, 3, 4, 5, 6, 7 units and 0.825. So again, pretty darn close to that 8. And that is the coordinate, the location on a real number line for 7.825. Okay, now if you were like me, I thought that was so fun. Okay, moving on. So now what we're going to do is get twice as difficult as this. A real number line only has one axis. It just has the horizontal. When we move into the coordinate plane, we have both the x and the y-axis. Okay, just as real numbers, these are all real numbers. Real numbers represent a location on a real number line. If you have what's called an ordered pair, and remember an ordered pair looks like this. You have x and then you have y. That represents a location on what's called a coordinate plane. So it's important that you know what a coordinate plane looks like. So below we're going to sketch a coordinate plane. In order to create a coordinate plane, you need a vertical line that is perpendicular. Perpendicular means that this angle right here is going to form a 90-degree angle with a horizontal axis. They want us to label the horizontal axis, the one that runs side to side, is called the x-axis. The vertical axis, the one that runs up and down, is called the y. Okay, in between that point where they cross, this is called the origin. Now, when you go ahead and graph a coordinate plane, notice that there are 4 different regions. Those 4 regions are called quadrants. This is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. So that's what a coordinate plane is. Now, when you're graphing an ordered pair, and that's what we are going to do right now, your x value tells you from the origin how you travel in a horizontal direction. If it's positive, you go to the right. If it's negative, you go to the left. The y value tells you how you travel on the y-axis, which runs up and down. If your y value is positive, you travel up. If your y value is negative, you travel downwards. So I'm going to go ahead and put some tick marks. 1, 2, 3, 4, 5. So that will be a positive 5. 1, 2, 3, 4, 5. Now going to the left, 1, 2, 3, 4, 5. This is negative 5 because it's the negative direction. 1, 2, 3, 4, 5. Again, this would also be negative 5. So if I am going to plot these points, 1, 4, this means I go to the right 1 and up 4. Right 1, up 1, 2, 3, 4. That's where your coordinate goes. The first value tells you left or right. This is negative, so I'm going to the left. The second value tells you up or down, so I'm going up. So I go to the left, 1, 2, 3, 4, up, 1, 2. That's where the coordinate would be. Now this one is negative, negative. So I'm going left 5 units and down 1 unit. This one I would go to the right 3 and down 5. So go to the right 1, 2, 3, down 5. That's where your coordinate would be. Now it's okay to have a 0. This means that I do not go left or right. The second value always tells you up or down, even if the first value is 0. Okay? The second one does not go to left or right. The second value is always up or down. So this means do not go left or right. Just go up 1, 2, 3. So that point is on the y-axis. So far we've looked at how do you graph on a real number line. That's just your visual graphic representation for real numbers. Coordinate plane, that is a visual representation and a location for every ordered pair. Kind of cool. It shows you where on the coordinate plane it would be in. And from there you could even say, okay, which section, which quadrant of that coordinate plane does that point fall? Okay. Scatter plots. In many application problems, remember application problems are those really cool story problems that we all love. Okay, so when you're doing application problems, your data is going to be plotted as just points on a coordinate plane. That means that you don't connect them. What you're going to do is have points and you look for a trend. Do the points tend to go upwards? Do they tend to go downwards? Are they just all over the place? Okay. This type of representation is called a scatter plot. So here's one fun thing we get to do today. We get to make a scatter plot. It says create a scatter plot of this data. This is data from the Federal Election Commission. It shows the total amount of money in millions of dollars contributed to all congressional candidates in the year shown. So remember when you have XY tables, the value on the top is X. The value on the bottom is Y. The reason why that's important is because as we go ahead and we want to make a scatter plot, we have to know which values to include. So the X value goes side to side. We are going to go from the years 1988 to 1996. So what I notice is it's every 2 years. So I'm going to include a break symbol. That means I'm not starting at 0. Okay, I am starting at 1988. Then I'm going to go 1990. I just have to make sure I'm evenly spaced. These are every 2 years, so we are 1992. And I'm just going to go 94, 96. Okay, so 1988, 1990, 1992, 1994, 1996. Okay, now here, again, you can use what's called a break symbol. What that means is that you're not starting at 0. My lowest amount in millions of dollars, and I'm going to go ahead and label that, millions of dollars. Nice. I wish I had $1 million, and I wish you guys all had millions of dollars too. That would be great. Back to the problem. So my smallest value is 276, and my largest value is 500. I'm going to go by 50s. I'm going to go 250, 300, 350, 400, 450, 500. And that is one thing that you want to really make sure that you're careful with. You always have to space evenly. We spaced evenly by 50s. Here we spaced evenly by 2s. I had to include a break symbol for both because I did not start at a 0. So that indicates that you zoomed in at a portion of the graph. If you do not include those break symbols, what you have created is called a misleading graph. Okay. Now as you graph this, you're just putting the coordinates. So at 1988, I'm going to 276. There's a point. 1990, I'm going a little bit higher, 284. 1992, whoa, we're going almost to 400. 1994, we're going almost or over 400. And 1996, we're going all the way up to 500. This is a scatter plot. And what we could do with this is look at the scenario. As the years increase, the dots tend to go upward. So what's happening is the scatter plot, it is the Federal Election Commission that shows the total amount of money contributed. So as the years go by, they're contributing more money to congressional candidates. That's the pattern. Super cool. So that's what a scatter plot is. Okay, moving on. A relation and its domain and range. Scientists, as well as social scientists, they spend a lot of time and a lot of money. They try to look at how two different quantities are related. Okay, so some things that they might study. Is a person's height correlated with his or her shoe size? You hear that quite often, that people who have larger feet are taller. Or you could hear it as, hey, tall people have bigger shoe sizes. Okay, so that's a relationship. Or how much money a person earns based off of how many years of college he or she completed. So that's where they try to encourage you guys to go to college because they want data that shows, hey, if you go to college more years, you're probably going to actually make some more money. So that's what social scientists typically spend their time and money looking at, trying to figure out those relations. Okay. In these examples, a relation, and that's what a relation is. A relation exists between two variables. It means that there's a relationship between two things. And often when we're talking about these relationships in math, the first value is the x variable. The second value is called the y variable. And it's just like we looked at on the previous page of notes. An ordered pair is a relation because it is a pairing of two different values, x and a y. Relations, or the pairing of two variables, they can be represented many ways. The first one is numerically. Numerically means you have like an ordered pair. So you're actually using numbers. You can represent them graphically, like we just did in a scatter plot. Wherever that coordinate is, that is the graphing location of that numerical representation. So they go hand in hand. The other thing you can do is represent them algebraically. And what that means is you might have a function like this, y equals x plus 2. So if x is 1, 1 plus 2, then y would be 3. If x is 2, then the y would be 4. So algebraically means that you have an equation where if you know an x value, you can fill it in and in turn find a y. One area of interest when they're studying a relation is the domain and range. Now that's something that we have studied in class before. Your domain are your x values. Your range make up your y values. One easy way to remember that, domain and range, if you go alphabetically, D comes before R in the alphabet, same thing with X and Y. Okay, so alphabetically, they do line up. If you are given a table like this, it says the table shows the heights and shoe sizes of 12 high school seniors. Represent this data using ordered pairs. So super cool. They want you to realize that you can take ordered pairs and create tables. You can take tables to create ordered pairs. So when you look at a table, if it is in a horizontal position, the top is the X, the bottom is the Y. So this would be 67, 8.5. So they're 67 inches tall, shoe size is 8.5. This student is 72 inches tall, and their shoe size is a 10. This student is 69 inches tall and has a size 12 shoe size. Then we have a 76 and a 12, and a 67 and a 10, and a 72 and an 11, and 67 and 7.5, 62.5, and the shoe size is a 5.5, 64.5, oh, and I almost forgot to do this, and the shoe size is an 8, 64 inches tall, shoe size is an 8.5, 62 inches tall, and they have a 6.5, and 62 and a 6. So this is one skill showing you that if you have a table of values, what you really have are relations represented numerically. This table can be representing using ordered pairs. They're using numbers. Now the domain and range. Remember the domain are the x values. So all of these values right here, you guys, these values make up the domain. Your range are the y values. So these values right here make up the range. So if you're ever given a table and it says to find the domain and the range, I am totally happy if you just do this. You have to know that the x values are the domain, so you could go ahead and label domain by the top and range by the bottom. You do not have to say domain 67, 72, 69, 76. You could, it would be fine, but save yourself some time. Just realize that all of the x's create the domain, all of the y's create the range. Okay, it says sometimes a rule, which is a statement or an equation, expresses one quantity in relation in terms to the other. And that's what they were talking about here. Algebraically means you have an equation. So you fill one value in, whether it be the x or the y, and then you could, from the equation, identify the other value. That's exactly what they're talking about. If I am given this relation, okay, relation, it is just a set of ordered pairs, a set of x's and y's, that sort of thing. We want to state the domain and the range. Okay, so here, this time it's in ordered pairs, so the domain, the x values. Domain are 0, the next ordered pair, it's a 1, then it's a 1. I could repeat it, but you don't have to. 1 is already listed. Then I have a 4, 4 again, 9, 9 again. So the domain, the values that I see in these ordered pairs in the x location are 0, 1, 4, and 9. The range, the y values, the first order pair has a 0 in the y. The second one has a 1, then a negative 1, then a 2, then a negative 2, then a 3, then a negative 3. So I could use ordered pairs and identify a domain and a range. Okay, it says state the domain and range, create a scatter plot. Okay, super cool. I'm going to go ahead and create a scatter plot. I'm going to have to go all the way to the right 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, good. The largest number I have going up or down is 3. And going to the left, I don't have to go to the left. Okay, so I have a point at, I'm going to use a different color here so we can see our points. 0, 0, 1, 1, 1, negative 1. Oh, cool. It's like a mirror image. Go to the right 1, 2, 3, 4, go up 2. Go to the right 4, go down 2. Go to the right 9. Cool. Go up 3. Go to the right 9, go down 3. So there's a scatter plot. From Algebra 2, check this out. It's a U-shaped graph. A U-shaped graph is called a parabola. But already we are stepping from Algebra 2 into Precalc, and it's a little bit tougher because in Algebra 2, all of our parabolas either open upwards or downwards. So here is your first time seeing a parabola that actually opens up to the side. Remember, when you are dealing with a parabola, it means you are going to have a power of 2. That's why it's important to understand the shape. Okay, so then it says, use ordered pairs to create a table. Well, we can do that too. Check this out. X, Y. Every ordered pair, I can just line up. So 0, 0, 1, 1, 1, negative 1, 4, 2, 4, negative 2, 9, 3. It's kind of cool to see all the different things that you can actually do with a set of ordered pairs. You could take the ordered pairs and you can graph them. You can identify domain and range. You can turn them into a table. What they want us to do now is to be able to figure out what is the relationship. And this is the harder part. How do you get from one value to the other? Okay, so 0, 0, they're the same. 1, 1, they're the same. 1, negative 1, 2s and 4s, 9s and 3s. Okay, so one thing that I notice, I know it's a parabola, which means it's a power of 2. That's what we learned in Algebra 2. It's a quadratic. You get a U-shaped graph. Your equation has to have a power of 2. So I know I'm going to either have to square the x to get the y or square the y to get the x. So if I try the x's, 0 squared is 0, 1 squared is 1, 1 squared is, not negative 1. Okay, let's see if it could be y squared. 0 squared is 0. 1 squared is 1. Negative 1 squared. Negative 1 times negative 1 is 1. 2 squared is 4. Negative 2 times negative 2 is 4. 3 squared is 9. Negative 3 squared, negative 3 times negative 3 is 9. So my equation, if I take the y value and square it, I get the x value. So that is a whole range of things you can do if you know a set of ordered pairs. Okay, last idea of the day, we're really going to go ahead and look at functions. A function is a relation. Okay, so a relation is a set of ordered pairs, and it can be shown many ways. Tables, scatter plots, ordered pairs. It is a pairing of an x and a y value. Okay, that's what a function or a relation is. In order for it to be a function, each x value can occur only one time. Every x value can only occur one time. That's the rule for it to be a function. So these are all relations. If you want to see if it's a function, you look at only the x values. Every x value can occur only once. So there's a 0, this is a 1, this is a 1. So no, this cannot be a function because, look at the 1s repeat, the 4s repeat, and the 9s repeat. Because 1s, 4s, and 9s repeat in the x location. You cannot have x's occur more than once in order for it to be a function. If I look at B, 0, 1, negative 1, 4, negative 4, 9, negative 9. Yes, that's a function because all x's occur only one time. Sorry, I'm talking and writing at the same time. I get excited. So here, if you look at the x values, every single x value is unique, meaning it's different. All x's occur only one time. Here, 0, 1, negative 1, 4, negative 4, 9, negative 9. Again, every x value is different. So yes, x's are all different. If they are all different, yes, it is a function. Last page. okay? The graph below defines a function whose rule is for input x, the output is a unique number y, so that the ordered pair xy is on the graph. All that's telling you is that they are going to give you either the input. If they say input, that means x. If they say output, that means y. They're going to give you one value. You are going to use the location on the graph to identify the other point. So find the output for the input 4. Input is x. So if your x value is 4, you go to the right 1, 2, 3, 4. Where's the y value? Oh, the y value is right here, so it's up 1, 2, 3. So your output is 3. Find the inputs, so we might have more than one, if the y is 0. So that means you don't go up or down. So here's one point where y is 0. The x value is 1, 2, 3 to the left, so -3. That's an input. Oh, here's another one. 0, 0. Here is another one. 2, 0. So your inputs would be 2, -3, and 0, because those are the locations on the graph where the y value was 0. Find the y value that corresponds to x equals -2. So if I go -2, check this out. Notice we have an open circle and a filled in circle. That means that the graph follows this, except for this is a hole, because the value at -2 is actually this filled in dot. So -2, it is not on the curve of the graph. It is the filled in point that is located at 3. State the domain and range of the function. Now notice this stops here and this stops here. Now your domain, left to right, -4 is the smallest x value. Remember, the domain is the x. So -4, it goes all the way up to right here. That would be 5. So your x values, left to right, they go in between -4 and 5. Your range, the lowest value is -2. Now it's y, the highest value that the graph goes is 3. So your range tells us that on the y-axis, all of our values on that graph go between -2 and 3. Last but not least, and again, yes, I know the notes are a little bit lengthy today. Typically, they'll be about 20-25 minutes, but there's so much information in section 1.1 because they wanted to make sure that you had a solid foundation before we move forward, okay? So don't let this set of notes worry you. Notes typically will probably be about 25 to 30, where this one's gonna go about 40, 45, okay? But let's end this section. We are looking at what's called function notation, and what's so cool is we get to actually start calculating now. Function notation is like this. It is a convenient shorthand that allows you to substitute in numbers for variables in a function or an algebraic expression. So notice this is f of x. This x tells us that in our function, our variable is an x. So when you write something like this, f of 3, notice that they replace the x in the notation with a 3. So I do the same thing here. I replace the x with the 3. Now it's order of operations. I would square the 3 before I'd add the 1. 3 squared is 9. 9 plus 1 is 10. So f of 3, if you take the f function, replace the x with a 3, your solution is the square root of 10. Let's go f of -5. So where the x is, you have to plug in a -5. Well, again, you square, order of operations, you do exponents before adding. -5 squared, -5 times -5 is positive 25. Now I can add the 1, making it 26. Perfect. Now f of 0. If I plug a 0 in where the x was, 0 squared is 0. 0 plus 1 is 1, and the square root of 1 is 1. Function notation. We're going to go ahead and do one more. This is a power of 2, which is kind of printed a little funky. So if this is my h function, my variable that I'm replacing is an x. So if I have h of the square root of 3, that means I go in here, and wherever there's an x, I have to put in the square root of 3 in its location. And notice this time I have 2 x's. Well, one cool thing, if you square a square root, that cancels. So this is 3 plus the square root of 3 minus 2. Now I can combine my 3 and negative 2 because they are like terms. They're both constants. So I have my square root of 3, positive 3 combined with a negative 2 is 1. So I have the square root of 3 plus 1. If I have h of negative 2, what I have to do is find every x and replace it with a negative 2. Order of operations, I'm going to do the exponents first. Negative 2 times negative 2 is positive 4. Remember, if you ever add a negative, it's the same as subtracting. Okay, so here I have 4 minus 2. It's 2. I just performed this operation to get the 2. 2 minus 2 is 0. So we did all that work for nothing. Ha 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 ha. Okay, last one. Sometimes, you guys, they will do this to you, and this is kind of wild. So if I have negative a going in for the x's plus negative a minus 2, the main thing is just to remember you can't always simplify down to a number. Here we're putting a variable in. You have to remember that if you square a negative, negative times a negative is a positive. So negative a times negative a is positive a squared. If you add a negative, it's the same as subtracting minus 2. This is your solution. Okay, now today was just a notes day because I knew that it would take kind of a long time. So you are done with pre-calculus for the day. Tomorrow is a day where you are going to practice these skills on your own. You have your notes to look at. You can always go back and rewatch this video. It's posted in Google Classroom. But your assignment, and you will have all class period tomorrow. If you are in the classroom, if you are at home, your pre-calc 4 tomorrow is to complete the assignment 1 to 34 on pages 10 to 12. Please keep your assignment in your math notebook. It is very helpful to keep all of your math together. Then if you are studying for a quiz or a test, you can always kind of page through your notebook and find the concepts that we have studied. One thing to know prior to moving on to the next section, we will be doing a quick quiz. Remember, quick quizzes are just a few questions to make sure that you are understanding what we went through today. I hope you had a great day of pre-calculus. I look forward to working with you soon. Take care.